Mrs. Mahoney's podcast 4.5, and we're going to keep looking at nuclear and compare a little bit about the nuclear particles and just do a few samples. This shouldn't be a long podcast unless I start to ramble, which you can't pause me or cut me off. I'll just try not to ramble. First thing we're going to look at is just actually I have a video clip that's just showing what alpha particles look like. No, back that up. I don't know what alpha particles. I can't show you a picture of what an alpha particle. I'm showing you evidence of an alpha particle. So, what we're looking at, get it started here. There's no talking, so I'm going to talk over it. These are actual little radiation sources. It's an alpha source. I actually used to do this in the lab, but it's too hard to get nuclear sources anymore because they want us to be safe and they're not very radioactive anymore. So what this is doing, it's actually shooting out the particles, but we've put this in a cold petri dish that has a black bottom, and then we put it on top, so this is a little bit of alcohol, and then we put it on some dry ice. So what you're seeing is like jet trails, like an airplane. You can see that that airplane has been there because it leaves behind a jet trail. You're seeing the jet trails of alpha particles. So looking at this closer, you can actually see this. Look at how it's shooting out these alpha particles. This is when you can start adding your own little sound effects. Pew, 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 that you're going in through the nuclear. And you can pretend that you're in science fiction because we're talking about radiation. But look at this. You can see that particles were being emitted, being kicked out from the source that was inside of this. So again, what you're seeing is it's just leaving little trails through that cold rubbing alcohol. And the only reason is just like, again, like the jet trails, because it's so cold up in the atmosphere, so we're not actually getting to see the alpha particles, but we're seeing evidence of the alpha particles. And this is what it means when it's saying it's emitted. They're literally being kicked out of the nucleus. They're being spit out of the nucleus so that it can change into something that's more stable. So that's why we call them alpha tracks. These are just tracks that are left behind when an alpha particle is emitted. Okay, at the bottom of page 11 is where we're at, and we need to know these three particles, and you need to know how they compare. That's where I've seen types of test questions show up. So the three particles I'm talking about, alpha, beta, gamma, three different ways. We need to know as far as their danger, their weight, and their speed. So let's look at first the danger. Okay, alpha particles are actually pretty harmless. They're pretty fast. They're still a very fast-moving nucleus, but because they're so heavy, because this is just a piece of paper. So we look. So this is just paper. Paper can stop an alpha particle. Your skin protects you from alpha particles. They're just too big, too heavy. They can't sustain the velocity to cause any damage. Next, in the middle, is my beta. Remember, that was just an electron, so it's a fast-moving electron. It will go through the paper, but wood can stop the beta. So wood can stop a beta particle. So again, it's kind of a little bit more dangerous than the alpha, but it's still pretty easy to protect from beta radiation. Then we have gamma. Now remember, gamma was pure energy, no mass, no weight, so it's just pure energy, so it is more dangerous. So when we talk about radiation, gamma rays, it takes concrete to stop the gamma radiation. So that's why when you see pictures of nuclear reactors and they have those big concrete, you see they kind of look like this, the nuclear reactors, and they're made of concrete. That's to stop the gamma radiation from getting out. So alpha, it has the least penetration, then beta, and then your gammas. We'll also compare them by weight. Well, alpha is the heaviest. It's kind of the slug. Then we have beta, and this is again alpha because remember it's the 4,2-He. It's like an alpha nucleus. Beta is just an electron, and then that gamma is just pure energy. So gamma is the lightest, Alpha is the heaviest. That's why it doesn't do as much damage. You would think, well, it's heavy, it should do more damage, but it can't go as fast. So let's look at the particle speed then. Because if I look at the speed, this alpha is slower. And because it's heavier, it can't sustain its speed to do much damage. Versus gamma is traveling already faster, and since it's traveling faster and it's lighter, it can do more damage because its momentum is going to keep it going. But again, you need to know the trends. And notice, beta is always in the middle. So alpha is the heaviest, then beta, and then the gamma. So comparing the speed, alpha is the slowest, and then beta, and then your gamma. So if you just remember, alpha is big, and it's slow, and it doesn't do much damage. Gamma is light, and it's fast, and it's going to do the most damage. So just make sure that if you have a question, it's going to ask you which is faster or which can do more damage. You need to recognize that gamma is the radiation that can do the most damage. Okay, we're just going to do some examples now of how we balance these, and then you'll be working on these on Monday. So to write the equation, keywords. This is saying what's it starting with, and I need to know what kind of decay. So since this is what it's starting with, I'm going to put it on the left side of the arrow, 56. Then you just have to find what is the atomic number for cobalt, 27. And I know that I said above 83 was radioactive, but many isotopes have radioactive isotopes in different elements. Usually it's in a very small percentage, but it's not there. What we're saying above 83 is the whole element is radioactive, versus below that you just have some isotopes that are radioactive. And so what's it saying? It's saying it's going to decay or lose an alpha particle. So then you have to do the math to figure out what's behind. Now remember, think of this like an equal sign. The arrow is like an equal sign. So this side of the arrow, and it means up on top and on the bottom, has to equal. So what do I have on top? I have 4 plus what, and what do I have over here? Equals 56. So as you can see that 56, let me write it down where I can actually see it. So I'm asking myself, okay, 56, and I have what? 4 plus what's missing? Well, that's 52. And then down on the bottom, you do the same thing on the numbers. I know it has to equal on the bottom 27, and this is just 2, so 2 plus what? 25. So that's where those numbers come from. 52, 25, and I use the periodic table. That is manganese. Okay, you don't have to show work on this as far as this work here. I'm just showing you where it comes from, and I won't be showing that work anymore. Okay, so cobalt 56. Same thing. This is what I'm starting with. And then I have to say, okay, what is it doing? Electron capture. And you go, oh yeah, capture. Capture means the electron is going on the left side, but the math is the same. I know the top has to equal. So 56 and 0, well, that's just 56. Well, 27 and a negative 1. So 27 plus a negative 1, that's 26, and that is iron. And you've balanced a nuclear equation because both sides, mass numbers and atomic numbers, are equal, and that's what we need, balance. Okay, so what do I have here? Polonium, 210. And again, we're going to have to look up the atomic number, and it's polonium, that's 84. What's it doing? It's undergoing a beta decay. So top, that's 210. Then over here, we have to make sure it's a negative 1. So what plus a negative 1 will equal 84? That is 85. So then what do? I use my periodic table. So find your periodic table. Look at it. What is element 85? That is acetine. And so that's your balanced equation. That's what you're creating. You're spitting out an alpha particle, and you're creating then acetine. Well, sometimes it can look a little bit different. This time I give you the ending and the starting and ending, but you have to figure out what's missing. We do it by the math doesn't change. So I always start, okay, what do I have? Berkelium 247, oops, 247, excuse me. So 247, and you look up the element number, so that's 97, and you're saying, okay, how is this going to change into curium 247? I did it again. Okay, that's a 4. 247, and the atomic number is 96. So then it's kind of the puzzle. Is it an alpha decay? Was it a beta decay? It was an electron capture. How did it go from this to this? Well, first thing I notice, it has to be something with no mass change. So I know I'm either losing an electron on this side or I'm adding an electron. Then I look at my atomic number. If I put the electron on this side, that would mean that I would see this decrease. And that's not happening. So what am I doing? I'm seeing this decrease. So okay, how did that happen? If I add an electron on this side, so 247 plus 0 is 247. 97 plus a negative 1 is how I get my 96. So this was by electron capture. Okay, here's another one. Let's just figure out, what did I start with? 152. Find it on the periodic table. That's element 63. And you're asking yourself, okay, how did it change to PM 148, which is atomic number 61? So you're looking for the missing piece, looking for what makes sense mathematically. And again, keeping in mind, you only have a couple of options. So what's the difference here? Again, what's the difference? 152 minus the 148, that's a difference of 4. 63, 61, what particle is that? That's He, and I know that the 2, that's the helium. So this underwent alpha decay. One more, the last one. Thallium, 207. Again, find the periodic table. Sometimes that's the hardest thing, finding the element on the periodic table. That's 81. And then we're going to lead, 207, which is 82. And again, how did that happen? So we know it's the top. It's got to be an electron because nothing changed on the mass. But this time the electron is going to be on the right, because I know 82 plus a negative 1 equals 81. So this underwent a beta decay. So in class on Monday, we're just going to do more practice of this. Sometimes I'll give you the equation. Sometimes it's going to be in words. We just have to get more confident in doing all kinds of reactions. I'll see you in class.